Welcome to the video presentation of the S+SSPR2020 paper, Estimating the Manifold Dimension of a Complex Network using Weyl's Law. This is co-authored by Luca Rossi from Queen Mary University of London and Andrea Torsello from Ca' Foscari University of Venice. Many real-world networks are embedded in either a 2- or a 3-dimensional space. Even when this embedding isn't as apparent as, for example, in a transportation network, it's been shown that the structural properties of a network can be explained by the geometry of the underlying space. For example, it has been shown that there is a relation between the curvature of the hyperbolic space underpinning certain networks and the presence of strong clustering or heterogeneous degree distributions. A number of researchers have looked at ways of estimating the dimension of these spaces. This is indeed also the problem we wanted to tackle in this work, as I'll explain in the next slides. Most of you will be familiar with the mathematical concept of a fractal dimension. In short, it can be seen as a way to measure the degree of self-similarity displayed by a certain pattern. Take for example the bottom right shape in this slide. Clearly this is created by recursively assembling units that bear a similarity to the whole shape. This is another classical example you may have already seen when reading about the concept of fractal dimension. As we see in the next slide, the fractal dimension of a pattern is related to the way the pattern changes as we look at it under increasingly smaller lenses. Now let epsilon be the side of a box. So in 1 dimension a line, in 2 dimensions the side of a square, and in 3 dimensions the side of a cube. Given a fixed volume, the number of boxes we need to cover this volume as we vary the size of the box is given by the relation shown in this slide, where d denotes the fractal dimension. Indeed, if we work out the math in this simple example, we can see that d is equal to the dimension of the underlying space, 1, 2, or 3 respectively. So far we only talked about general patterns, shapes. Can something like the fractal dimension be computed for a graph as well? Well, the answer is yes, and there are 2 main methods to estimate the fractal dimension of a network: the box counting and the cluster growing methods. Now, the idea of the box counting method is similar to what we have already seen a few slides ago. Here we were trying to count how many boxes of a given size were needed to cover the contour of the island. Similarly, given a network, we want to try and cover it with quote-unquote boxes of varying sizes. By box, here we mean a subgraph, and its size is going to be its diameter. Then we can recover the fractal dimension of the graph thanks to the following scaling relation. So NB is the minimum number of boxes of size LB required to cover the network, while DB is the estimated fractal dimension. This is indeed a simple and widely used method. However, it's easy to see that it can be mapped to an NP-hard graph coloring problem, and as such, well, it's hard to solve and requires us to look for a locally optimal solution using some sort of heuristic. An alternative method is to select a number of random seed nodes and grow non-overlapping clusters of radius LC around them. Then the following relation holds, where MC is the average mass of the clusters for a given radius and DC is the fractal dimension. Now, the drawback of this method is that on networks with non-homogeneous degree distributions, by picking random seeds we have a high probability of including hubs, ending up with the biased estimate of the fractal dimension. In this paper, we look for an alternative approach, and to this end we make use of a well-known mathematical result known as Weyl law. This is an equation describing the asymptotic behavior of the eigenvalues of the Laplacian on an unbounded domain omega in d dimensions. So here in this equation, n lambda is a function that counts the number of eigenvalues less than or equal to lambda, and d is the dimension of the space, and the remaining bits depend on the volume of the domain. For sufficiently large lambda, we can rewrite this into the following relation between n of lambda and lambda, where we replaced all those other bits with k. Then we can take the logarithm of this and obtain a linear relation between the two sides, where the dimension of the space D can be easily estimated given a few sample points. So this brings us to our simple idea. Given a graph G, we compute the spectrum of its Laplacian and we use linear regression to estimate the dimension D of the underlying space, given the previous equation. For this to work, we have to assume that the graph is manifold. So in other words, that the graph can be seen as a discrete representation of the continuous underlying space. The figure here illustrates the estimation process, where given the eigenvalues of the Laplacian and the corresponding values of n, we perform linear regression on a range of points and estimate D. And note also that we need to select a range, because Weyl law doesn't hold for low frequencies, and also at the same time high frequencies capture local variations of the dimension near the graph boundary, and this can affect negatively our estimate if we don't exclude them. With this framework in place, we can easily also incorporate information on edge weights and node attributes. So real-valued edge weights are naturally incorporated into the Laplacian, and node attributes can be converted into edge weights by measuring the similarity between every pair of connected nodes. Finally, it's important to stress that given a manifold graph, the dimension D we estimate is in fact equivalent to its fractal dimension, and that's why I talked about the fractal dimension before. So really, when we talk about the manifold dimension of a manifold graph, we mean its fractal dimension, and vice versa. So we test our approach now on a number of different synthetic and real-world graphs that I'll describe in the next slides. Most importantly, we compare our method to a method for computing the fractal dimension of a graph, which is known as maximum excluded mass burning, or MAMB in short. This is a widely used method to estimate the fractal dimension of graphs, belongs to the box counting family, and most importantly, the implementation was readily available on GitHub. As synthetic graphs, we consider the Lonely graphs and the hypercubes. For both, we know the ground truth dimension. It's 2 for the Lonely graphs, while for the hypercubes, we consider graphs of dimension 2, 3, and 4. This table here in the slide shows the estimated dimension by our method and MAMB. And we can see that our estimates are consistently closer to the ground truth, while MAMB tends to underestimate. And this shouldn't be surprising, because remember, it's a box counting method. And for these methods, their heuristic nature, because they're solving and trying to solve an NP-hard problem, means that the minimum number of boxes that we find is an overestimation usually, and therefore the fractal dimension that follows is going to be an underestimation. Here's another example, this time highlighting the results on the hypercube with dimension 2. We then also wanted to test our method on a set of synthetic graphs that are by construction fractal. There's a formula at the bottom of this slide that gives us the fractal dimension of the graphs given the parameters they're built with. But these graphs are not manifold. Now, for increasing values of V, according to the formula at the bottom, the fractal dimension of the graphs should increase. And this is correctly captured by MAMB, although the value again is underestimated. Our method instead estimates the decreasing value of the dimension as V increases, but this shouldn't be surprising because we notice that for high values of V, we have this increasing presence of long unidimensional string-like structures in the graph, which basically end up dominating the value of the manifold dimension. Indeed, as we said already, these are fractal, not manifold graphs. We then test our method on real-world networks. These are 1 square mile maps where the nodes are road intersections and the edges are road themselves. As such, we expect that this type of graphs to be inherently two-dimensional networks. This is correctly captured by our estimate, while MAMB consistently underestimates the value of the dimension. The values in italic here, by the way, refer to the estimate we get when the edge weights, so the length of the road segment, are taken into account. Here's another quick example on the streets of Venice. And as a final experiment, we considered four other types of real-world networks. So the top plots show a relatively clear manifold structure here on the left and right, and correspond on the left to the power grid network of the US, and to the right, the adjacency graph of the most common nouns and adjectives in the novel David Copperfield. The bottom plots, on the other hand, show, in addition to the usual boundary effects toward the right of the plots, show trends that are harder to reconcile with the expected linear trends that we should see if the graphs were indeed manifold. So to conclude, we have proposed a simple yet effective method to estimate the manifold dimension of a graph based on Weyl's law. We have tested it on synthetic and real-world graphs and generally performed well. There's a number of questions open that are mentioned here in the slides. For example, can we automate the selection of the spectral range that we use to fit the linear regression? Or if we look at larger graphs, can the local dimension of a community tell us something about its function or properties in relation to the rest of the graph? So these are open questions, but that's all for this video. If you have any additional questions, please don't hesitate to get in touch during S+SSPR, the online discussion session, or simply drop me an email at the address shown in the slide. Bye!